Thank you everyone for coming to our Innovative Series seminar, which is the last for 2015. Sarah has planned already most of the seminars for 2016, so check the website and please stay tuned. So before introducing our speaker today, I need to go through some housekeeping points. Please make sure you sign in. There is a paper sheet in the back of the room. Please RSVP for the next seminar so that we can better prepare for the next session. Online participants, please keep mics muted unless asking a question and keep video turned off, as well as use the chat feature in BlueJeans if you have technical questions. So as I said, this is our last presentation of 2015. We will return on January 8th with Applied Genomics, next generation sequencing in the clinical field. And all our previous presentations are available on our website, DE-CTR.org. So I'm very excited today to introduce Dr. Sebastian Cioaba. Dr. Cioaba is Associate Professor in the Department of Mathematics at University of Delaware. He obtained his master and his PhD in mathematics from Queen's University at Kingston in Canada, and his Bachelor of Science in Mathematics and Computer Sciences from University of Bucharest in Romania. He is on the editorial board of several mathematics journals. He's a prolific writer and has written several books and chapters and many manuscripts and papers. Has a long experience as an educator and has supervised and mentored multiple undergrad and graduate students in their research, and has given talks and conducted workshops all over the world. So I think we are very lucky to have you here, and we are very curious about all the network and network medicine. Thank you so much for coming.
Thank you very much. I'm very happy to be here. I want to thank Dr. Weintraub for allowing me to come give a talk to your group, and to Sarah for helping me with setting up for this talk. It's always great to come back to Christiana Hospital. My older son was born here about 5 years ago, and it always kind of, no matter what I come here for, that always pops into my head all the time. He was 5 weeks early. He was born here in November 2000, about 5 years ago. Spent 4 days in NICU for jaundice and stuff. Everything was fine, and he's now he's high and he's growing. He's probably in 5 years he's going to be taller than me. So thank you all for coming here. I'm gonna I work in graph theory at University of Delaware. So graph theory is the abstract modeling of networks, and so I will give you an introduction first to graph theory and to networks, and then I will tell you some things that I understand about how networks are applied in medicine, and there are many things that I still don't understand. And I would like you to see this talk as a kind of an open invitation. If you feel that any of the topics here could be used in your research, or could be used in anything that you have encountered, please feel free to talk to me about it. I would like to collaborate with you, or any of you, on something involving networks and network medicine. So networks, I'll start with a brief introduction, about networks. So the beginning goes back to Euler in 1736. So Euler lived alive 1707 to 1783. He's a famous Swiss mathematician, one of the biggest mathematicians of the world. At that time, he was a mathematician at the court of King of Prussia. And there was this problem about the bridges in the town Königsberg, which is now Kaliningrad. And this is a picture. So you have 4 masses of land, which are denoted by gray. You have a river that goes through the town, and you have 7 bridges in red that connect them. So the question is, can you start anywhere on these 4 masses of land, go through every bridge exactly once, and go back to where you started? Now, what Euler realized is that this looks like a geometric problem, but it's a different kind of geometry, in the sense that you don't care that much about lengths and measurements. You don't care how deep the river is. You don't care how long the bridge is, and how big the area of these lands are. What you care is more of a geometry of position. You care how are things related to each other. So this mass of land, you can represent it by a dot, And this island here, you can represent it by a dot, and all it matters is that there are two bridges between them, so each bridge you represent it by a curve between them. And the same way, so you're going to have four masses of land, the north, the south, this island on the west, and this one on the east. So this is basically the way you would represent it. And then all the bridges, you have 7 bridges, they become these connections. And now the question is, it's one of these puzzles you give a child to do. Pick a dot, go on each line exactly once, and go back to where you started. There's actually even an app now. I gave you actually this morning. Yes, it's called One Touch Draw. So you can look it up. Yes, One Touch Draw. Actually, the students in my Introduction to Discrete Math class, a 9 a.m. class that I had this morning at University of Delaware, I talked about this problem. If you have a way of going through every edge exactly, the segments and the curves are called edges. If you can go through every edge exactly once and come back to where you started, that is called an Eulerian circuit, in honor of Euler. And not every graph has an Eulerian circuit. In this situation, you cannot do it. And what is the reason why you cannot do it? Well, if you would be able to do it, then when you walk on these edges, let's say you start here, you go on this edge, you enter this node. When you leave the node, you cannot use the edge again. So you have to come out on a different node. So every time you go through a node, you're using 2 connections. So if at the end of the day you have to go through every connection and go back to where you started, that would mean that every node would have to have 2 plus 2 plus 2, something number of connections. So every node would have to have an even number of connections at it. So in this situation, that's not the case, so you cannot do it. And there's a different part where if I give you a network in which everybody has an even degree, how do you actually do it? And you can always. So that's so this app, One Touch Draw, essentially will give you these kind of networks, and it asks you go from one node to the other, or go from one node and come back to where you start. It's essentially Euler circuits. That's all it is. Sorry. Now, you can go more further with kids' game, and you can go to maps. Every map you can color it with 4 colors, such that any 2 countries that share, or states that share a border, they get different colors. Now, is this a fact, or is this fiction? Is this provable or not? It turns out that it's it is a kid's game when you start, but it becomes quite serious. And this was one of the most famous, maybe the most famous problem in graph theory, and it has something to do with dots and lines. And I will show you in a second how it works. This was proved actually by two mathematicians at University of Urbana-Champaign in Illinois, Kenneth Happel and Wolfgang Haken, in 1976. They showed that every map can be colored with 4 colors, such that any 2 countries that share a border get different colors. The amazing thing about their proof is that it also used computer. So they could do it for most of the cases, but they had some configurations for which they needed to use computer. So these days, people have refined their arguments, and they've reduced the role of the computer in it. I mean, some people felt uneasy about using computer in a mathematical proof. Nevertheless, this is an amazing. I think Kenneth Happel just passed away 2 years ago. So how do you actually relate it to these dots and lines? Well, the problem is about coloring a map. It's actually a problem of coloring dots in this graph, because what you do for every country, this is a snapshot in Central Africa. So for every country, you represent it by a dot. And whenever you have share a border, you draw a line between it. So instead of looking at the map, you're looking basically at a bunch of dots and connections between them. And what you want to do? You want to assign each dot a color such that whenever 2 dots are connected, they get different colors. So countries that get the same color, like this one and this one, they should not be connected. So they should be kind of what I call independent. You have, among the countries that have the same color, there are no connections between them. And these things now, this forms a basis of a huge area of research in graph theory about graph coloring. These are a special kind of graphs. These are what are called planar graphs, in the sense that you can lay them on the plane such that you see you have no crossings. You have no crossings between the edges. But there are more complicated graphs for which it's impossible for you to put them on the plane without crossings. And these things have application in when people design circuits. They don't want to have crossings and stuff like that. So this is basically how you can formalize the concept of map coloring as a graph coloring problem. Now, you go to dots and lines, and even Hollywood thought this was interesting. So this is a snapshot from Good Will Hunting. I don't know if you remember the movie. In Good Will Hunting, he's a janitor at MIT or Harvard, and basically during the, between cleaning this and that, he's drawing trees. These are trees. These are special type of graph that appear a lot in chemistry when you draw your maybe hydrocarbons and stuff like that, that have the property that if you take one of them, any two nodes are connected by exactly one path. So they're basically connected things, but you have no cycles. That's what we call a tree. So that's they appear in many places. And this is, if you remember in the movie, it's very hard to catch because it goes very fast, but people after that, they took a snapshot of it. So the story of, it is that you have this famous professor at the university who's challenging the students, giving them this amazingly hard problem. And whoever is going to, he talks about Fields Medal, which is kind of like the Nobel, equivalent of Nobel Prize in mathematics and so on if you solve this problem. Well, if you actually read what it says, I mean, not to say that Hollywood is exaggerating. This is actually pretty simple. So the first thing, this is the graph. Again, I did this in undergraduate class on Wednesday. So we did number 1 and number 2. Number 3 and 4, you actually have to teach them what generating function is, and that takes a little bit more time. It's not very sophisticated, but that's more like a beginning, maybe graduate or advanced undergraduate students will know. Adjacency matrix. And this is important because I will come back to it a bit later. So if this is the graph or network, what you do with the adjacency matrix, you label the nodes. They're already labeled. So now you're going to make a matrix whose rows and columns are labeled by the vertices. So I didn't write it, but in this matrix, the first row and the first column, they correspond to node 1. Second row, second column correspond to node 2, 3, and so on. And what you do now, you take node 1 and you look. Node 1, how many connections does it have to itself? It has 0. So you put a 0 in the row 1 and column 1. Node 1, how many connections does it have with 2? It has 1. So you put a 1 there. Node 1, no connection to 3, so that's why the 0 is there. And node 1 has 1 connection to 4, so you put a 1. So you do this thing for every. So essentially, if you have the network, it's the same thing as having this matrix. So basically, this is a symmetric matrix. Like what happens on the row 1, it happens on column 1. So this is very important because in mathematics, in linear algebra, we like symmetric matrices because what you can do with them, this thing called spectral decomposition. You can decompose them. You have nice eigenvectors. Everything is beautiful. Maybe singular value decomposition, stuff like that. Maybe. So this is basically answer to question 1. Question 2, giving the number of 3-step walks. So a 3-step walk is you start at a node and you walk on the connections and you take three steps. So if I go 1, 2, 2, 3, 3, 2, that is a walk. 1, 2, 2, 4, 4, 3, that is not a walk because from 4 to 3 I don't have a connection. So it will be a sequence of 4. If you have 3-step walks, you have 4 nodes such that any 2 consecutive nodes, they're actually connected together. And actually, how do you get this matrix? You get it from this matrix by raising it to power 3. So this is a basic fact we teach them in algebraic graph theory. You take this matrix, you raise it to power 100, you get 100-step walks. Because for walks, I don't care if like when you're going for a walk, you can go back and forth on the same road many times. Like you don't have to go to different edges, different nodes. You can go back and forth as long as you're walking on the. So I'll come back to this connection with linear algebra. Now, this is, if that doesn't convince you, this is more serious stuff. How do you find your perfect matching? So you have many situations, job, people looking for jobs and their qualifications, matching, man and woman, and you have certain preferences. Can you match every man with a woman that they prefer and so on? So you could have this is a special kind of graph which is called bipartite. Bipartite because you can split the nodes into 2 classes. In this case, the women and the men, such that inside the classes, there are no connections. So also, if I were to color this, I need just two colors. So I give everybody at the bottom one color, everybody at the top one color, and there are no connection. So bipartite graphs are things that we like in graph theory because they're very, very simple. If you have cycles in bipartite graphs, the cycles are always going to be even. You don't have odd cycles. That's another way of thinking of it. So for this one, it's actually, there are many algorithms, and there's a theorem actually called marriage theorem. It's Hall's marriage theorem, which tells you when you actually have a perfect matching, in such a bipartite graph. And in this case, I'm not sure if you can see, but there's some edges that are connected red, so it works here. So this theory of matchings, it's a huge area of research in mathematics, computer science, and even economics. And I'm not sure if you knew, about a couple of years ago, the Nobel Prize in Economics was awarded to Lloyd Shapley and Alvin Roth for the theory of stable allocations and the practice of market design. So stable allocation, that's what Shapley did. So if you look online, he's basically considered the father of cooperative game theory. I'm not sure if you remember the movie Beautiful Life with John Nash. John Nash, the father of non-cooperative game theory. You're basically on your own. You're trying to do the best for you. Cooperative game theory, people kind of communicate with each other and stuff like that. Both Shapley and John Nash, they graduated at Princeton, and they had the same supervisor, Albert Tucker. His name is in all optimization and so on. So what he did, he has a paper in American Mathematical Monthly, which is this mathematical journal for elementary mathematics, like mathematics that can be understood by a high school student. Elementary doesn't mean easy. It just means that you don't need to know what the sheaf is or what the C-star algebras are or something like that. It's something very, very, very simple, elementary. But in their paper, it's called College Admissions and Stable Matchings. And the college admission is about how do you have students applying to colleges, and the students rank the colleges according to preferences, and colleges rank the students according to their preferences. How do you make a matching that is stable, in the sense that there is no pair of a student and a college that prefer each other more than they prefer to their actual matching? In another scenario, this is this national resident matching program in which the residents rank the hospitals rank the residents. So how do you make sure they are not playing games about waiting for the letter? I mean, I know about this from Grey's Anatomy, so maybe it's, yeah. But essentially, they have this algorithm which is called Gale-Shapley algorithm, which is very simple. You can basically explain it to an undergraduate, in which you can get a stable matching. And it depends if the doctors make the proposal versus if the hospitals make the proposal. The outcomes can be different. In summary, it pays to be bold. So better for doctors for them to make the proposal instead the other way around. And anyway, so in this paper, it's like a 3-page paper. They say, well, we studied this math problem. We thought it was interesting. We have no idea. They put it in a nice way, but they say, basically, we are in the world of mathematical make-believe. We have no idea if this is useful, but we hope it will be useful. Well, Alvin Roth, so he's an economist, I think at Harvard or that. So basically, he dug into this, and he actually found out that the National Resident Matching Program that was used in the US was using a version of this algorithm since the 40s, but they were not aware of each other. And then with the ideas from this algorithm, stable matchings, he went, for example, he was asked to help with the New York City Department of Education, matching students going into high schools with high schools accepting them, because the rate of satisfaction was very low. So he went in and he applied these techniques. And now I think he's using these techniques to do for transplants, in the sense that maybe the husband needs an organ. The wife would donate her organ, but she's not compatible. So she will donate it to somebody else if that person is going to donate it to somebody else. And at the end, somehow the cycle, they even made, I think, a path of like, or cycle of something like 8, like to go around so that you satisfy many people. So anyway, it's very interesting. Now, going back to social networks and other things. So there's this network with Bacon number where the nodes are the actors. And So these are kind of closely related. So over here, you would have a network of actors and movies, and you put a node between them if the actor is in that movie. And then over here, you just take one side. This will appear a bit later. The same type of construction will be later. This is a bipartite graph. You have movies on one side, and you have actors on the other side. So you put an actor in the movie if the actor is in the movie. Now, if I just put the actors and I want to join them if they've been in the movie, you look here and you say, well, Kevin Bacon and John Lithgow, they've been here, so you connect them here. So it's basically you just keep that side of it. And now you go back about 6 degrees of Bacon. So everybody's supposed, if you're a serious actor, you're supposed to be within 6 steps of Kevin Bacon. Yeah, and this goes back to Stanley Milgram, who was doing social sciences in the 60s. And so he had this experiment where people from far away, like Omaha or something like that, were sending letters to people. So they were given a target, somebody maybe in Boston, and they say, you don't know that person in Boston, but please send this letter to someone that you think might be closer to that person in Boston. So let's see how quickly the letters, and the person that gets the letter would do the same thing. Well, I don't know that person, but maybe I'll send it to somebody that I know. So the idea is that we have this kind of phenomenon of a small world network that we are connected by pretty much everybody else in this world by in at most six steps. So there are other, I forgot which newspaper did some kind of experiment connecting Marlon Brando live with some kebab vendor in Germany or something like that. So again, you get this weird connection. The vendor had a cousin that emigrated to US, and then in US you kind of work your way through. So this was kind of the experiment. And this was very small experiment. Like they sent like 200 letters. Most of them were never returned and so on. These days, like there were people who actually did this experiment again with like much many more letters. And now, so you know, networks appear in all these social networks. This is a snapshot of Twitter. And actually about 6 degrees, like about 4 years ago, I'm not sure what the number is now, but Facebook said, you know, it's not 6 degrees of separation, it's about that much. And what does that mean? Well, actually, with their data, so this is the data, I think, in the whole world, and this is the data in the United States, what they can do is they can look at any two persons, and they can find the shortest path between those two people. I mean, you can do that. And so they can average that. So basically what they did, they calculated, so you see, most people are, what, about 5 connections apart and so on. So you have these kind of percentages about how people are, how far they are from each other. So obviously, you know, even if you have 500 friends, that's not that much in the whole scheme of things. So yeah, so so this small world phenomenon, it appears in many, like pretty much everywhere in this kind of real life networks, like social networks, and it will appear in the networks that people study in medicine, the ones that I've seen. And the last one, as an example, is Google. So essentially their key idea was, okay, we want to rank elements of a network. So we use the links, the hyperlinks that you get from a site as a vote for your importance, for your page rank. Basically, they want to rank the nodes. So if you get a link from Yahoo, that should be much more worth it than 500 links from the fake web pages that you created just so that you increase your page rank. So when you write this down, the basic idea is that the importance of a link is proportional to the importances of the nodes that point to you. Okay, and it looks like it's a circular argument. Well, what about the importance of the nodes that point to me? Where does that? Well, it's the same thing. It's given by the importance of the things that point to you. So you write this down, and what it becomes a matrix equation. It's basically about an eigenvalue and an eigenvector. It's essentially linear algebra. And in their study, the original paper of Sergey Brin and Larry Page, the founders of Google, it's online. It's a paper in some computer science conference in Australia, I think late 90s. And they basically give you kind of the whole, now people have written books about it and so on, but they explain how this works. And they actually give themselves a parameter that they can juggle with and try to do experiments to see what it works best. So they can weight these matrices in a certain way. I'm not going to talk about it now, but they say, well, we think that alpha equals 0.85 for this gives us good results. I mean, so this idea of using linear algebra to ranking things, it wasn't new, but they had the idea to put it into this scenario, and how do you actually carry out with a huge web graph? That's also another, like it's a huge. But at the bottom of it, it's basically linear algebra. Basically straightforward. Now in network medicine, so I've been interested in how do people use these things to network medicine, and in this part, like I said, you might know a lot more than me about some of these things. So this is a review paper by Barabashi, and Loscalzo in Nature Reviews Genetics. So by the way, I can send you or Sarafe a list of all the references that I use, so you can read them for yourselves and so on. So they basically want to give an overview of the organizing principles of this field that they call network medicine. They start by basically describing that networks are everywhere. Protein interactions, metabolic networks, all these networks that are there. Just mentioned one of them. So this is from a paper by Rual and some other people. So basically here, you take as nodes your proteins, and you join them if you have some physical interaction between them. And there's a lot of work into basically creating these databases and all these acronyms. They're in their survey paper, and you can have a look at what they all mean. So at this point, a lot of work is into creating these huge databases and these keeping track of the connections between these proteins. Now, so the key hypothesis at their basis of their study is that like things interact in a very complex manner. So you cannot when you're looking for an abnormality, you shouldn't look just for one thing. You should look for things that interact in this kind of in this complex fashion. So this is in their paper. This is our key hypothesis of our study, that things interact in a complex network, so it makes sense to study the way they interact. And they see network medicine as a platform to basically explore the complexity of a disease and the relation between maybe different phenotypes. And as advances, like why would you do that? Well, they claim that they're essential for identifying new disease genes, covering the significance of various other diseases, and to come up with drugs to take care of this. So let me give you some example of how people have studied these things. So there's this paper in PNAS 2005 by Go, and again Barabashi is involved as well there. So this is called the Human Disease Network. And so what they did, they went to the online Mendelian inheritance in men. There is this database that you probably are more familiar with than I am, OIMM. And they had 1,284. This is just a snapshot. I'll show you a bigger picture later. So you have over 1,000 disorders and over 1,500 disease genes. And you put on this side you put the disease, and on this side you put the genes, and you put a connection between them if that gene has something to do with them. And now the fatter the nodes, it happens when this has many connections. So basically the size of the node is proportional to the number of connections. So in these pictures, they say they have things like deafness that has a degree of 41. So deafness would be 41 genes in their stuff, leukemia 37, colon cancer 34, and so on. And so this is basically kind of like this bipartite graph, movies and actors. And now what they do is they split it into two parts. On one part, we're going to put just the diseases, the disorders. So you basically take just this part, and you connect two nodes but you see, like some of these connections are fatter than others because this breast cancer, and I'm not sure what is there. It's another prostate cancer. Yeah, the number of common genes it's larger. So you basically weighted by the number of genes that are implicated in both. And the fatter again the node, the larger the number of connections coming into it. And the colors are basically, they say that we use colors to kind of put diseases in the same kind of family. And here, you do the same thing, but you do it for genes. So on this side, the degrees can go as high as 40 or something like that. On this side, the genes can be involved, other genes up to 10. So there's a little bit of difference on which side you're looking. And so this is kind of what they call the human disease network. And I'm not sure if you can see, because I tried to fit this in here, and maybe, so this is deafness. Yeah, I'm not sure if you can see. I can send you the reference for all of them, and these are the size of the connection. So this is cancer, colon cancer, leukemia, and so you can map. And then if you go to the genes, it's so cardiovascular. It's this color. So maybe this. So you have this kind of. Again, you already kind of get an idea. Okay, this is not very. I mean, you knew that without me this picture. But this is not a very nice, symmetric and rounded network. You have these clusters all over the place. Okay, so again, these are like they study basically what they did. They did many studies of this network. So basically, the one with the previous one, the human disease network has about 12,084 nodes. 800 of them have at least one connection outside. There is 516 that form a big component. So not everything is connected to everything. And the degree distribution is quite broad, and I'll come back to that. So, and again, there's a lot of study that they do in terms of clusters, statistics on these networks, and so on. So that's now in this review paper by Lo Scalzo, Barabashi, and Lubach, they basically state that we believe that all these biological networks have these properties. Small or phenomena is that you have short paths between any pairs of, 6 degrees of separation, 4.7 or something like that, and it seems to be the case. You have high degrees of modules, what they call modules, and here this is something that maybe I understand from the graph theory network property, which is when I talk about topological models, I can see that there are these clusters. You see these clusters, but they define also what are called functional modules, which they're trying to kind of identify a functional module in terms of what these things are doing in the body and so on. So this is more medical stuff that I don't understand that well. Now here for the power law degree distribution, so the number of vertices of degree k is proportional to k to some negative constant. And so essentially the picture kind of shows. If you had like a random network in which everything was equally likely, all the connections, then your degree distribution would be normal, the number of connections. But here it's a power law. So it means that you have these very few kind of highly connected hubs, and then most of them are kind of on the periphery. So these highly linked nodes, they call them hubs. And the big thing is, how do I prove that these are, I mean, kind of intuition would say, okay, these are associated with some essential elements of the networks, being disorders, being genes, and so on. So that's something that appears there. Now they talk about motifs. These are like small subgraphs that appear kind of more or less frequently than in these networks. And some other measures of how do you measure how important your node is? Like how many things, if I want to go from X to Y, how many times do I have to pass through these nodes? So that's kind of the betweenness. How much of a bottleneck that node is. Like again, a kind of a measure of importance. Now, so about these hubs and diseases, this is another, I think it's in Science. I think it's a letter to Science by Barabashi and two authors. So they look at, I took Latin in school for 1 year, but I still couldn't pronounce this. And my wife, who's a biochemist, says, okay, just call it yeast. And So they study this network where you have, it's a protein, so you have 1,800 nodes connected by this, so it looks like this. So they wanted to say, well, if I look at these hubs, are they actually the most important ones? So they actually could take them out, the hubs, and measure the effect that has on the network. So they basically, the claim here is that this basically shows that for this network, the nodes with the highest degree are actually the most important. I mean, in a sense, yeah, I believe that, but yeah. So they present it as an evidence. Now there are different types of networks. So these are like comorbidity networks. So again, it's Barabashi and some co-authors. So here what they did, they have the medical records. So that's how I heard about ICD-9. Well, this is 9. So they say that they got some Medicare records of over 30 million. So over 30 million records of 13 million people, about 10,000 diseases. So they basically make a map of the diseases. So the nodes are going to be the diseases. And you want to measure, okay, like this disease, how many times do they appear together in a person? And it's actually, that happens more often than it should be if just the diseases were kind of like independent. They're trying to measure how related these diseases are. So they came up with these two measures. So one is the relative risk. So if you have two diseases, I and J, the relative risk of observing the I and J affecting the same patient is going to be the number of patients affected by both times the whole size of the people divided by the ones you can write it as a frequency, as a percentage of the people affected by both divided by the product of the probabilities of each of them, if you know, it's in a different way. And then this is kind of like this statistical correlation that they also use, this Pearson correlation of variables that they also look at. And here they draw a picture of so the age distribution, and then kind of like how these things differ in their network, and then they plot it once against each other. So they feel, okay, clearly they're not random. Obviously, I mean, the RRJ is involved in here, so they're related. And now with these two measures, so they basically do some more. They discuss that basically one overestimates certain rare diseases versus underestimating certain more common diseases. So this is kind of more statistical part. So for each of them, basically they construct what they this phenotype disease network, PDN. And the way it's constructed, so I try to put, these are all in the same thing. So this is for the RR network. So what they did with PDN consider, so they only kept the links with RRJ bigger than 20. So why do you put 20 and you don't put 15? Again, these are things that you can play with. And here, it's also like they do these significant links with 5 bigger than 0.0. I have a picture with them in the same. So this is the first one. So this is the picture with relative risk, how they, according to these relative risks, things are connected to each other. And then this is the other picture. And they have all this explanation about types of, you know, heart disease and all that stuff. And again, for these things, like there's a lot of work in terms of statistics about studying this network, and they do quite a bit in their paper. And one thing they observe, so they have, I'll give you the kind of their objectives and kind of what they claim they do in a second. But this is a picture of how the network differs from according to ethnicity, from black male versus to white male, and they found that it differs. So that was one of the things that they set up to do at the beginning. Well, how do these things differ from different genders, different ethnicity? And they show that. So this is the part where it's more pronounced for black male, and here for. So like again, the nodes are the diseases, and like the bigger kind of the edge between them, the more likely they occur together than normal. Than kind of like if they were completely independent. So this is kind of that. So basically, what their evidence is for The first one, that the patient will develop disease close in network to those that they already have that disease. The progression of the disease happens along the links of the network, and it's different from different genders and ethnicities. And if you're diagnosed with a disease that's highly connected, you tend to die sooner than the ones that's kind of to the periphery. And diseases that tend to be preceded by others in this network tend to be more connected than diseases that precede others and are associated with a higher degree. So I know these are some of the work that. Now the work of them was basically other people were inspired by this, and these are some scientists in Austria. So they had the data from 2 years in Austria of the whole country, and they look at the prevalence of a certain number of diseases. And actually, the story that I read at the beginning was that they were given this data, and people in Austria were planning ahead, and they were asked, well, what happened if our funding would be cut by a third? Would we be able to provide the same kind of care? I read their paper, and I haven't seen the answer to this question. They do all kinds of things. So again, what they do, again, they are going to do this comorbidity network where you put the diseases and you link them if the probability of suffering two diseases together is larger than the product of suffering each of them individually. And so they have this, they have all kinds of findings. And one thing they do, and it's kind of, again, speaking, it makes sense. They look at, they split them female and male, and they look at the network according to age. And the diseases for kids, they're very kind of isolated, and there's like one single cluster. As people get older, there are various clusters around, and when they're old, everything is. Yeah. Yes, you know exactly. Yeah. So people could say, well, we knew this, but maybe they say this with nicer pictures. Or, yeah. No, they have other things that there's so much data in some of these papers. Like they talk about European Union, the age of people, by 2050 they have all these predictions that people are going to get older and all this stuff. So. It's really interesting stuff, but so I don't know everything in all these papers. I'm just giving you some glimpse of what I think it's fascinating. Now also, like in other places, now you have this RNA kind of you have this bipartite graphs between microRNAs and genes. So this is Los Calzo and co-authors. So here they're looking about the interaction between this. So the microRNA are on the inside, and the genes are on the outside. So it's again this kind of bipartite graph where you're basically measuring the effect of microRNA on these genes. So they're doing this kind of again for all these are like networks in maybe different universities. So you're looking at some parameters might be of interest for one network. They might be of interest. Some other parameters might be of interest for other networks. And even in brains now, they're basically kind of discretizing the connections, and they're looking at comparing different brain networks with different size and connectivity using graph theory. Is one. There is again in the same kind of series of Los Calzo, Barabashi, and Bache, there is a review paper about how this is used in so this is kind of the picture. You kind of split things up and you try to connect them according to the data that you have from MRI, and you make these networks, and again create an associated matrix, adjacency matrix, the matrix that we discussed. So like from my impression from the outside, I understand the networks part. I don't understand the medicine and all that part in that much detail. That this is kind of at the beginning, and there is a very nice article in Quanta Magazine. So Quanta Magazine is this newsletter of the Simons Foundation, which is offering a lot of grants for math, physics, and various other sciences. And they have this article about, that's kind of how I got started in this. I read the newsletter, and I thought this is very interesting. And they talked about Barabashi and Los Calzo and some other people. And there's a quote there about Los Calzo mentioning that, okay, with this network medicine, you have some people that are truly believe in it, believe in the data, and you believe the network, and you do what the network does. There are people that say, well, forget about it. We have been doing things the way for many years, and there are people in between that. So I don't know. I mean, it's really interesting, and I think worth investigating further. And it might be applicable to other areas that you might know more than. And so I will stop here, and I will basically, one thing that there are some papers that I haven't gone into details. There are 3 papers in this review paper in which they mention actual attempts to create drugs. I can give you the links about people trying to use the networks to go select some drug targets and so on. One thing that I haven't seen here anywhere, so all the analysis of networks has been done at this kind of what is called combinatorial level, in the sense that, okay, this is more important because I'm counting the connections and so on. You do all these degree distribution. One thing that I haven't seen, and it might be worth pursuing, is to do this kind of spectral analysis where you look at the adjacency matrix and you rank things according to eigenvector. I mentioned, when I mentioned about Google, about how Google moved away, basically we don't rank you according to how many friends you have. We're going to go into this matrix, we're going to calculate what is an eigenvector, and the eigenvector is going to tell us the real. So in terms of spectral analysis, I haven't seen much, and my research is a lot in eigenvalues, eigenvector, spectral graphs, so I would be interested to discuss it with you. I'll stop here. Thank you very much. Yes.
This is spectacular. So I just will ask you to speculate a little bit more on how this could be used in therapeutics. And I'll give you this is just for
You're
fun.
asking the wrong doctor.
It's all for fun. So
I mean,
I'll give you an example, and let's see what we can do with it. There's a common disease that we're very concerned about here, us and our colleagues at Nemours, called familial hypercholesterolemia. It occurs in 1 in 250 people, so it's common. But there are like 1,600 genetic abnormalities that can cause it. And people sometimes don't have one of them, they have multiple ones. And there are basically 5 drugs to treat hypercholesterolemia, basically 5. 2 when the people have 2 of the genes, and 3 when they have 1 of the genes. But we had a talk about the genetics of this recently, and I said to Sam Getty, you probably know it, at Moores, I said, which of these are going to be good? Which of these abnormalities are going to be better for one drug than the other? And he said, we don't know. So do you think this kind of analysis could help us?
I mean, so again, one thing that one can do, if you see a picture like this, yes, you have some things clear, like you have these big nodes, but maybe when I look at smaller things, like when you cannot distinguish about 2 nodes, like how do I measure if this is more important? Like if I were to map out like this network of genes involved in here, so that's one thing. Like how do you map it out? Like when do you connect 2 genes together? When they, I mean, this part comes from medical. Then if you have this network, like there are tools, like these spectral tools can tell you that actually this node is more important than this one, even though they have the same number of neighbors and it looks like they are on the same page. You go into this spectral analysis, and this spectral analysis, in my opinion, it can be quite revealing. So that is, I think that might be one thing to do to actually, okay, how do I actually, because I showed this to Bruce Bowman yesterday at UD, just to kind of if you can see if it's okay. And he was asking me something about cancer genes, these versus the other. And I had the same answer. Well, why don't you try to basically get this, because these networks are not very big. You can plug nowadays. We can do this on a laptop. You plug this thing into a MATLAB. You will get your eigenvectors, and then you can play with it and try to see the meaning. Like, well, from this eigenvector entry, I can read that this is more important than the other. So I think this is something that should be done. I mean, definitely at the theoretical level, it should be. Yes.
Thank you so much for the talk. It was great. As I'm looking at this diagram here, not to make it too much to healthcare, but I noticed in the cancer area, there's so many connections, and I wonder if that's relying upon the amount of literature that exists in that field. Maybe certain areas, certain clusters may not have as much research, or at least the level of rigor of research that you need to make these connections. Could you speak as to how do you capture that, or the
So basically, in these networks, the way they did it, they have this again, like, I mean, they comment in this review paper, they comment that these databases are continuously curated. So they basically say, oh, okay, at some point we thought that this is linked to this, but maybe it's not the case. So they're always, they admit that maybe they're not completely perfect, the connection. But basically the way this is built, again, you have this connection between this gene is involved. So it depends, of course, of what people know about, like what is involved in something like here. Well, we only know these genes. They could be more, but this is basically represents kind of the state of art in the database at that point, whenever they pull it out. Today, if we look and we try to build something, it might be, you know what I mean? It could be this, but they could be links together. So again, like there is something to be kind of aware of, that not everything is, you know, but I'm assuming there are very good people that take care of these databases. So for most part, I think everything should be, you know, be fine. But again, it depends on what we know. Like you know, what you know, I know less about maybe this being connected to this or something. So yes.
Well, I actually have a network of questions, but let me just. This seems very similar to statistical methods like related around cluster analysis, correspondence analysis, structural equation modeling. Is this sort of the same thing, or are there differences, or does this just handle bigger data sets?
Well, I mean, that's the thing. Like for these networks, from what I see, they're different directions. So there's like a theoretical direction where they say all these networks have this power law degree, they have clusters and so on, and we can study the properties as a theoretical thing. And then for specific networks, basically different authors will go look at different, you know what I mean? Will go look at different things. Like these people in Austria, they wanted to see how this network evolved over time because that was their, you know, their interest. Here, it's basically this kind of, you have these diseases connected to each other because there are many genes appearing in both of them. So maybe from the medical point of view, you would ask different questions here than you would ask for that network. So yes, and cluster analysis and stuff like that. Yes, I mean, again, in their survey paper, review paper, they mentioned these notions of modules, which is kind of like a cluster. But they break the module into different kinds. So there's a topological thing, which is kind of, okay, what do I have here? And I can measure that kind of mathematically. I say, well, what are clusters? Clusters are a snapshot of the network where maybe I have much more connections than everywhere else. You know what I mean? But why is this a cluster? And maybe I don't consider the whole thing here a cluster. So that's when you have to come up with different measures of, you know what I mean? Like if you just look at the network, you can say, well, this is dense. Why don't I make the whole thing? You know, it's in a sense is a cluster. So you have these kind of various different quantitative measures of cluster. And mathematics actually, and spectral methods are very good at actually when you go in and try to read the clusters from like eigenvectors and stuff like that, they will tell you. You can go and split it into clusters. And now they have this notion that I don't completely understand of functional cluster. And I, you know, like it's in the, and you know, if somebody would like to read this, I'll be happy to discuss it, where they basically say, okay, these are things that actually do the same thing. So, because for me, if I look at the network, you know, maybe I think of it kind of without the, in a sense, the labels. I just study the mathematics and I study the nodes, how do you split them, and all these properties. But from your perspective, or you know, the doctor's perspective, how do you actually, you know, what do these things mean?
Well, one of the issues with the methods like cluster analysis is that you reach a level of complexity where it becomes useless.
Yes.
And that looks to me like that could easily happen here.
Again,
things are so complex. It's
Yes.
like, well, so maybe
Yes.
the doctors think, well, okay, let's just do this. Maybe that's the best thing to do.
yeah, I mean, again, for these things, like I'm not, this is what the research showed. This is what, I mean, the key hypothesis is that things are related in a very messy way. You know what I mean? And they're trying, in a sense, I think they're trying to kind of make, okay, can we put an order into this a little bit? Keep this one with this ones, this one with this ones. It's not as clear as everything is on a line, and I can put the shoes there, and so on. So, yeah, I mean, I think, yes.
So possibly there's not a theory of everything.
No, there's not a theory of everything. That's, yeah.
Just a quick comment to comment on Paul's comment. I think what is really fascinating is the relationship between genes and disease and how they intercorrelate. And if you can find that several diseases share the same genes that you really didn't think about earlier, I mean, it really can lead to big advances both in therapeutic and knowledge of medicine and how it works.
Yeah, and I mean, this is the first step. You take the data that you have and you put it like this. And maybe you will see something, maybe things will be messy, but you try to at least make sense of, like the problem that you were mentioning about, so many genes and stuff like that. You try to somehow relate it to each other. Is there a way, quantitative way? Because you can argue about this relative risk. Okay, maybe you can measure it different way. And why do you put bigger than 20 and you don't put bigger than 10? And why do you put 5 bigger than 0.06 and not 0.5? I mean, these things that have to be tried, and you see what data you get. Like, again, for Google is not a mathematical theorem that nobody can prove something that Google will always get you the result that you get all the time. However, for whatever parameters they choose when they tinker with their search, it works well for most of most people. Yeah. I mean, there is exact science about but sometimes you kind of do what you can. Thank you.